Okay, so hello everyone, I'm Renato Nascimento, and today I'll present this work about Generative Adversarial Minority Oversampling by Mulek et al. So the presentation will follow as with the introduction. We will cover a quick overview about Generative Adversarial neural networks. We will talk about some related works. Then I'll present the proposed method and show some experiments and results in different data sets. So the problem that this paper is trying to tackle is the problem known as class imbalance, which consists that in real life situations the distribution of samples is most likely skewed. That means you're going to see more one class than another class. And they even show here for us a toy example where the blue dots would be the majority class and the red dots is the minority class. And most learning algorithms, they will produce an inductive bias favoring the majority class. What that means, in cyan here and yellow would be the classifier, and then you can see that the model would be missing some points of the minority class, wrongly classifying this data set. This is very common to find across different data sets. Here's an example of a video data set for action recognition, and it has different classes and different categories of classes. For example, actions, person to person, person to object are pose. As you can see here on the left, some actions are seen way more often than the other ones. For example, person-to-person action to watch a person, luckily, is way more often seen than kick a person, right? So that's very common in data sets. And I want to bring also an example of real-world applications and industrial applications. So this on the left, for example, this is a Kaggle challenge that Airbus released a couple years ago, where you have to detect ship on the satellite images on the ocean, and as you might imagine, there's often more empty images with no ship than images with ship. So almost 80% of the images, they didn't have any ship on it. So it's a highly imbalanced data set to classify. And also in industrial applications, for example, with the real data set, here on the right we have images from a wind turbine gearbox, borescope inspection, where we have two examples with some faults. On the right, those are debris dents, and on the left, oil droplets. So when you collect those data, you will see mostly more data, nominal data with oil droplets than debris, and the model might have difficulties to actually correctly classify the faults on those data sets. And how can we handle this problem with this kind of data set? There is multiple techniques to do so. We can do, for example, cost tuning, where you set different costs to different loss functions to different classes, putting a higher cost in the minority class, for example. You could also undersampling, where you select a subset of classes which are balanced on a bigger data set, which is not that great because you end up losing some of the data that you have at your disposal to train. And what we'll be covering on this work is oversampling technique. That usually cannot be directly applied in end-to-end deep learning system, meaning first you have to oversample your data set and then you go training your classifier. This proposed method, they propose an end-to-end technique using generative adversarial networks to do oversampling. And what does that mean is, as on the green points, as you can see here, you basically suggest new points, artificial points belongs to the minority class, trying to aid the model to better classify this data set. So a quick overview in what are a generative adversarial network. It was first introduced by Goodfellow et al. In 2014, and the main idea is that you have two neural networks. You have the discriminator and the generator. It's known as a two-player adversarial game, where you have the discriminator that is trying to the string between real and fake image generated by the generator, and the generator is trying to fool the discriminator, generate image that the discriminator would wrongly classify as a real sample. And for that, you have a loss for the discriminator and a loss for the generator as well. Give an example how that works on with some example. For example, with MNIST dataset, which are the handwritten digits, as we all know, the way this algorithm works is you draw some samples from the real dataset, and of course you have the tag saying that the dataset's real, and then you have a random input to the generator. That generator, which is not trained yet, generate a random output and is classified as fake. And then for a couple steps, you train the discriminator first, and once you do that, then this number of steps, by the way, is a hyperparameter that you can tweak. Once you do that for a while, then you start to train the generator and the generator loss. And if you keep doing this, you have a new, you draw a new batch of samples from the real data set. You have a new random input. Now the weights of the generator are already tweaked with the loss that you did before. They are generate better results. The discriminator is still correct classifying the real and fake. If you keep doing this for a while, what's going to happen is you're going to generate an image that's close enough to a real image, and then the discriminator is not going to be able to distinguish anymore between real and fake. That's the general idea how generative adversarial networks work. So the way that we train this is with a minimax loss function. In this case, we are showing the cross entropy one, and the idea is we want to maximize the probability of the discriminator correctly classify an image as real. So since we are maximizing, we get this loss, and we do a gradient ascending on that, on the back propagation, only for the weights on the discriminator. We do this on the first step, as I said before. Once you do this for a while, then we train the generator. The generator is trying to minimize the probability of the generator generates a fake image. So therefore, you use a gradient descent back propagation, right? And it's important to note here, even though that we are using the weights from the discriminator on this step of the algorithm, usually we don't train the weights of the discriminator. You only train the weights of the generator. So related works. How can you oversample data sets? So this is a known method by doing that. Was first introduced in 2002 and is widely used still. So the idea is you choose the k nearest neighbors of a point, and then you choose, you distribute points using the Euclidean distance between those points. For example, on this left here, if we look at the purple points, and it belongs to the purple class, then you could choose, I don't know, usually it's 5, so 5 nearest points to that point, and then you distribute points, calculate the distance between those points, and that's how oversampled data set would look like on the right. As you can see, on some points that were missing points, now we have artificial points added there. This is one of the old techniques. Again, this you need to do prior your data, right? You first do that, then you train your classifier. More recently, using GANs, there's this work which is called Conditional Generative Adversarial Network, which basically is you add the label information to your GAN. So on the beginning, for the output of your generator, you also add the label for that class. Same idea you do for the discriminators. You have the image, and also you have the label. And then, likewise, using cross entropy, you train trying to minimize that. You minimize the generator and maximize the probability of the discriminator as well. We will see some results. They compare their results of the proposed methods with that method as well. So And this is the proposed method. Basically, it is a 3-player adversarial game where you have a convex generator, classifier network, and a discriminator. And the idea is that the generator needs to fool both the classifier and the discriminator. I will try to go over this schematic once we go item by item, right? So first, the convex generator. So the idea is to generate new points only as a convex combination of the existing points from the minority class in questions, right? So, and they do this by using more than one block. So they have a conditional transient mapping unit, which is basically a density connection where they have the label and the noise they generate. And then they connect the output of that unit with the instance generator unit, which is this yellow block here, which they would have one per each minority class that they are oversampling. So if you're oversampling a 9 class, in this example of the most of the examples that we are looking here, you're going to have one block of block for each class over here. And then you switch as you go to that class. To train that, it's also use the cross entropy loss. We are going to see that they also test different laws, and we're going to show the difference of the results of those as well. And then again, it's a min-max game where you minimize the generator and maximizing the classifier. But the problem here, and here's are the loss functions apply, right, to the classification problem with multiple classes. The problem is if you run that for a while, if you run that enough, you're going to end up generate points that are location within the majority, right? Like those green ones. And then you're going to improve the classification for the majority class, but you're not going to help at all with the minority. So to overcome that, the authors also propose then the additional discriminator, which is used to ensure the generated points they do not fall outside the distribution of the minority class. So would be this additional red line and red block here, where they have the label, also the output vector from the instance generation unit, and they have to classify as real or fake. And then becomes a 3-player minimax game where they have to minimize the loss on the generator and maximize the loss both for the classifier as we saw before, and now for the discriminator as they call Q, and that will be the loss they're now maximizing. It's worth to remember here when you're training the generator, although on the forward pass you go through those different networks, you are only tweaking the weights from the generator once you're on the generator step. And also they try different laws, which is known by literature, that have best results for GANs. So they try to do the least square laws as well. And here is how they apply. For example, L1 to 5 is the loss for the classifier, 5 to 6 for the discriminator, and 7 to 9 is the loss for the generator. Likewise, when you train the generator, you don't tweak the weights from the classifier and discriminator. So they test this method in multiple different data sets. They did on the regular MNIST and on the fashion MNIST. Regular MNIST is the handwritten that, as we know, and the fashion MNIST is the same size, 28 by 28 grayscale with 10 classes. It has images like objects like t-shirt, boots, and so far. Those data sets, they are balanced. So they create a subset imbalancing that data set artificially. And the way they did, they just order by the label index and select different number of images for each class, as follow on the illustration here on the left. Those far creating an imbalancing ratio for this case of 100. That means if you divide the number of images that you have for the largest by the smallest one. They will evaluate those data sets using two metrics: average class specific accuracy, which is the specific accuracy for each class, and then you average it out, and also geometric mean. So some experiments here, they are showing what comes out of the generator for the MNIST. What is interesting to see here, for example, the traditional method actually generates quite good images, right? Although you have to do that in a separate step. As I said, you generate the oversample, and then you go over a convolutional neural network to generate those images, and you end up with good results. And then here we have the conditional again, and it shows that.
Hey guys, sit down. Thank you.
Thank you. It's seen that we can, for the majority class, in other words, the class that has more samples, it actually create good images, but for the minority one, not that much. They have some problems with this other generator, and on the right here, we are showing their two proposed methods. This one is without the discriminator, and with the discriminator, they actually generate quite good images. And this is the results that they achieve with MNIST and MNIST fashion. We can see that both losses, even cross entropy and least square, they actually improve, but they achieve very good results with the least square loss. And compare with the other methods, like I said, the baseline convolutional neural network, then oversampling with a smooth method, or oversampling with the other methods, they achieve quite better results in comparison. They also test this data set on, this method on different data sets, on the C410, on the Street View house number as well. Interesting to notice, those are RGB images, so we have now 3 channels, right? 32 by 32, also still with 10 classes. On the right here, we can see how this C410 samples look like and how the Street View house number samples look like. Again, those data sets are balanced, so they artificially create a subset of imbalanced data by applying that division here, following the label index. And for both data sets, creating an imbalance rate of 56.25, using the same metrics to evaluate the quality of the method. They showed that although it did not perform as well as on a simpler data set as MNIST as expected, but it did improve the other methods compared quite well. And here they are only showing the results for the least square. So they also try data sets with a higher resolution to see how that method apply on bigger images, right? So they try with the Celeb A, which is 64 by 64, also RGB. They took 5 classes of this data set. If I'm not mistaken, is like the class they took is like blonde, bald, simpler classes like that. And they also did a subset. Oh, then they did 2 subsets of this one. They did one with less samples and one with more samples. So a small and a large subset following this class selection and this imbalance ratio. So 100 on the smaller and 37.33 on the larger. They also did this for a different data set, LSUN, which is much bigger images, 224 by 224. Also, they select only 5 classes of this data set, which are natural images. Those are exterior images and interior images, right? They did likewise small and large subsets of this data set. Looking at the results, they also show that, this one is interesting because they show the training results as well, showing that most of the other methods, they overfit quite well. And their method, although it doesn't overfit that much, it still overfits a little bit, but achieve much better result on the testing, both for the small and for the large data set. Trying to prove that this method was good for different data sets and size of data set as well. One last point that's worth to notice is their method. They use a convolutional neural network to extract vectors, features from the image on the beginning. Thus far, the generator actually never generates an image within the network, right? So if some application requires the samples to be generated, so you save those samples, they come up with this additional step where they get the feature extractor image that they already have on their method, and they couple that with the convolutional layer so they can generate the image. And then they did that for the CFR10, Fashionist, Street View, House Numbers, and Celebs Mall. And you can see the quality of the images on the right here. And they use this metric to evaluate how good the images are generated, which is a metric that's used for evaluate the quality of gains. As low it means that the model is better, and it quite achieve better results than the other method to compare. This code is available on GitHub, so anybody that wants to try, it is there, and that will be all. Any questions?